Thank you very much, everybody, for having come back for the second part of this talk. So let's get started, right? So let me just remind you of the overview from yesterday, although there is now an additional first item, namely an addition to yesterday's talk that I'll begin with. Then I shall outline the proof of the main theorem, which is the main part of this talk, that is the joint work with the Piotr Kosmita. Then I'm going to talk a bit about automatic continuity of homomorphisms from B of X. That will be sort of linking to the final part of the talk, namely uniqueness of algebra norm on all quotients of B of X by its closed ideals. This is a joint work with my student Max Arnold. But let's get started with the addition. So I should thank Kanya for having pointed out that the list I gave yesterday of CK spaces, all of whose complementary subspaces are known, was, well, the list as such is correct, but it is incomplete. So the list had in it C0, well, an index set of arbitrary cardinality, then continuous functions up to omega to the omega and L infinity. But there are more results to be added. In particular, and quite embarrassing really, of course, we have C0 of Ka, this Rovka space I've been discussing, where A is a special almost disjoint family that admits only few operators, because of course, as Piotr already showed back in 2005, well, basically this Banach space only has one kind of non-trivial decomposition as a direct sum, namely you can write it as a direct sum of itself plus C0, and it's isomorphic to hyperplanes. So really there are only two isomorphism types there of complemented subspaces, namely the space itself and C0. So actually in that respect, this space is similar to this one up here, the continuous function up to omega to the omega, except of course this one is isomorphic to its square, whereas this one manifestly isn't. It can have a clear role a little bit later. But then the real reason for Tomek's interest in this topic is that he, together with Bill Johnson and Gideon Shechtman, they did a substantial study of the space that is usually called L infinity superscript C of gamma. So you take an uncountable set gamma, you look at L infinity of gamma, but you then restrict to those, say, uncountable sequences that have countable support. So that gives you a closed subspace of L infinity gamma. Obviously, if gamma was countable, you could do this, then you just get the usual L infinity back, of course, right? So anyway, this Banach space here, so Johnson, Kanya, Shechtman, they showed that every infinite dimensional complementary subspace of it is, well, either L infinity, as I say, you may see that as a limiting case of L infinity C for a countable index set, or it is L infinity C for a say a subset delta, an uncountable subset delta of gamma, or in other words, any index set here really that has cardinality no greater than gamma. All right, and this list is to be continued on the next page, because finally Bill, Tomek, and Gideon also observed that actually you can kind of combine the spaces in this list in the following way, that if you have K scattered and L, such as C of L is a Grothendieck space, so that would be like L infinity or L infinity C gamma, okay, and you know all the complementary subspaces of both C of K and C and L, then if you take their disjoint union, you can also know what they are. Okay, and well, if you are uncomfortable about this, what this disjoint union is, well, isomorphically is simply the direct sum of C of K and C of L, all right? And this will allow me to continue my slightly sloppy way of treating CK spaces, because some of them, of course, are not really CK spaces, as in they live on A, and they are C0 of K, where K is only locally compact, all right? So, for example, you can take, for the scattered part, you can take C0 of gamma. That's one of those which is technically not really a CK space, but it's isomorphically a CK space, so we are satisfied with that. Or you can take Benjamini's space, so continuous functions up to omega to the omega, or you can take Piotr's space, the C0 of Ka, where your uncountable almost disjoint family admits only a few operators. Okay, so they all fall in the first category. The underlying space is scattered. All right, and we know what the closed, all the complementary subspaces are. Okay, so what about the second part? What else can we take? Well, we can take an infinity or an infinity C for some uncountable index set, say epsilon. So I chose a different letter here just to not clash with the gamma up there. All right, so that's the that I think is the full story of what is known about CK spaces, where you can actually describe all the complemented subspaces. And of course, the context of this was this impressive result of Banach and Alberto Salguero that I hope we might hear more about later today, namely that there is a CK space which has a complemented subspace which is not isomorphic to any CK space. Okay, so that was the extra information here. Back to the main line of the talk. So my first aim today is to try and outline this new proof that Piotr and I produced within ZFZ of the fact that you can find an uncountable almost disjoint family A such that C0 of the associated Mirovka space has few operators in the sense that every operator on it is a scalar multiple of the identity plus an operator with separable range, or probably an operator that factors to 0. All right, and let me just do a bit of a recap from yesterday. So since this Mirovka space is scattered, well, if you take an operator on C0K, take a function in C0Ka, and you take a point in Ka, and then you apply t to the function, of course, that gives you a new continuous function, so you can evaluate that at S. Well, we can just write that as the duality bracket with a point evaluation. Then we can move the operator t over by duality, and then we use the fact that the dual of C0 Ka is just little L1, so all the measures are point masses. So therefore, the duality bracket simply looks like summing over all points, taking the measure at the point mass of t, and then multiplying with the function value at t. And then that's it, right? That's how you do this calculation. And for that reason, we kind of think of T star of the point mass delta S, and then taken at the point, the singleton set T. We think of that as a matrix representation of T, right? Because this looks like here we have a matrix. Here we are summing along, we sum along a row. So we think of the function F as like a column, right? And you do matrix multiplication. That's the picture you want to have in mind here. Although, of course, the index set of your matrix is rather wild. It is uncountable in particular, right? So that is our matrix representation. Let me also remind you of the way I think of my space Ka. So we have these isolated points Xn, and then we have these points, extra points we add, the YAs. And there's one for each A in the almost disjoint family. And the rule we have is that Xn converges to YA as n goes to infinity through the set A. And somebody asked me yesterday a bit about the intuition behind this. And I think the way I would like to suggest you want to look at this, right, is that we have up here, normally say, if you compact it by the natural numbers, right, you just add infinity and every unbounded sequence converges to the same point. Here we do something very different because we add all these uncountably many points here, YA, YB, YC, YB. Of course, I'm not going to succeed because there are uncountably many of them even, right? But for each of them, we essentially assign a unique sequence that converges to it, namely the sequence Xn, where n runs through A. So the picture is that when you have n in A, then you have that kind of behavior. When you have n in B, you have this behavior. And when you have n in C, you have that behavior, and so on and so forth. And of course, it's not true that these sequences are totally disjoint, as you might imagine from my picture, right? Because they will obviously have to overlap a lot, but only each pair of sequences, right? Because we are in not almost disjoint family, so each pair of them will only have finitely many points in common. So that's somehow the picture you want to bear in mind, I think, and why this space is different from usual compactifications and so on that you might look at. And in particular, of course, it means that if you take a sequence of Xn's, but where the n's are not eventually in one of the sets in the almost disjoint family, that sequence will not converge, right? Anyway, so we now introduce, because we think, I mean, these matrix representations we had of our operators up there, they're good because they give like a perfect, I mean, a one-to-one representation of operators, right? We have all kept all the information, but the problem is our index set has cardinality of continuum usually, so that's far too much to keep track of. We need a smaller index set, and therefore we introduce the reduced matrix of our operator T, and now we forget about the points YA, the extra ones we added at the top, and we only focus on what happens at these isolated points, the xn's and the xn and xk, okay? So now we get a matrix that is indexed by the natural numbers, and in case you wonder, that dot there, that's just a full stop at the end of the sentence, it's not a decoration on the letter N. All right, so basically the reason why this is a good idea is that all the YAs can be reached by convergence of these xn's, by suitable choices of xn's, right? So we sort of have enough, it's like having almost like a dense set. That's how you want to think of these matrices. And I'll give you shortly a calculation to try and substantiate a little bit why these reduced matrices, they don't keep all information, but they sort of keep enough to get us going here. And of course, the point is that there are only continuum many of these matrices. So ultimately, we shall enumerate them and then do a transfinite induction to kind of kill them off, to rule them out as possible matrices of operators. That's the sort of strategy of this. All right. So what can we say about these reduced matrices? Well, basically, they have the following property, that if you take one of these matrices of that form, then if you sum along a row, okay, the absolute values of the entries, then that will be summable, okay? And if you then take the sup over all these row sums, you get a finite number. So the rows are absolutely summable, and there's a uniform bound on them, all right? And that's what we call the norm of our matrix here, all right? So they all belong to that set there. And well, if you come from operator theory, you may spot that this is exactly the matrices which represent operators from C0 into L infinity via the sort of natural matrix multiplication formula, right? So if you have a function f in C0, an element of C0, right? How do you find its value? So this is now an element of L infinity, right? So how do you find the value at k? Well, you simply do the usual matrix multiplication formula there. All right. But let me just observe that you could actually do that not just for f in C0, you can do it for f in L infinity. So in other words, our matrix induced operator here extends to L infinity. All right, and where the matrices in this letter boldface M, they're the transposes of operators on little l1, or in other words, the weak star continuous operators on L infinity. So this is just to say, if you're looking at this set and it looks kind of familiar, it is familiar, it plays a role, but actually what we're doing, we don't really exploit that. Some of the intuition comes from that fact, but we don't really need that in our construction. Okay. So let's see. Now, as I told you, I want to try and give you a calculation that I hope might give you an idea why these reduced matrices are useful when you want to analyze operators. So we take an operator T, we take two sets from the almost disjoint family A. Well, then the indicator function of the sort of a standard neighborhood of the set A is, of course, a continuous function vanishing at infinity, right? So UA here, I remind you, that's the full neighborhood of YA, so just all the points xn in this sequence that converges to YA, so in runs through the set A there. All right, so since that's a continuous function, we can obviously apply the operator T to it to get another continuous function, so we can evaluate it at xk for any k, say, in the set B. And now the point is that if I pick my k, so I mean, I can do this, let's see if I can get this to work here, right? I can, of course, this exists just because this is a continuous function, so I'm allowed to evaluate it at xk. But now, if I pick K to be in my second set B from the almost disjoint family, and I let it tend to infinity, then of course the limit is the point YB, all right? And therefore, by continuity of this function, this thing here will converge to that guy there, all right? So, why is that important? Well, now we pick the left-hand side of the convergence there, and I was simply trying to calculate what that is, and then in the end, we'll bring everything together. So how can we calculate this? Well, first we just do duality, then we move T over by duality again, all right? And then we use Rudin's theorem, the fact that the dual of C0 Ka is just little 1. So the duality bracket in practice means that you take the measure evaluated at the singleton sets, and then you pair that up with the function values at the corresponding points, and you sum over all T in Ka. So that was the matrix representation we had before in a special case. But of course, evaluating an indicator function at a point is dead easy, right? Because it's 1 when you're in the set and it's 0 otherwise. And you will now see I'm in slightly better shape now because of that, because at least now this sum is, it's clearly now I have reduced the index set here to a countable set. Of course, since it's converged, I know this also was only non-zero on a countable set, but it kind of is more manageable now. Because in particular, I know what the set UA is. It has two parts. It has an infinite part, namely the xn's, and then it has the point YA. All right. And due to my lack of typesetting skills, I want this under brace later on, but ignore it for now. Okay. So basically, I break it up into the two parts: the infinite parts, the n in A, where the point T here will just be xn. So that's this part up there. All right, and then at the end, I have the extra point I added there. Okay, and now for the under brace, well, you will see that this is exactly how I defined my reduced matrix of T. This is the knth element of that matrix. Okay, so if you've forgotten what that matrix looked like, well, this was precisely how I defined it. All right, and so what significance of that? Well, I remember, again, by Rudin's theorem, that T star of delta K is an element of little l1, all right? So in other words, in particular, it must have countable support. So in other words, there can be at most countably many sets A in script A, where this value here is non-zero, all right? And well, of course, if I take a countable union of countable sets, it remains countable. Okay, call that set AT. And note here that I was just hesitating slightly for a second, but actually this is not a typo. Up here, from the start of the calculation, A, you should think of as fixed. But now I sort of say let A be general. Okay, so this was just the connection there. So indeed, I do mean for all A is no longer necessarily fixed here. All right, and then now if I apply the previous calculation to A, which is not in this set here, all right, so outside of that countable set, well, by what I just did up here, right, I just copied down what that said, all right, because in this case, when I stay outside of that set, right, this term vanishes. That's exactly how I defined A sub T, right? That if you're not in A sub T, then this is necessarily 0. So in other words, I get rid of this extra term there. All right. And well, of course, you can calculate that by usual matrix methods, right? What is the, if you're summing along the kth row, only taking those in A, well, that's the same as applying your matrix to the indicator function of A, and then you want to pick out the value in the kth row of it, so that's just evaluating a k. So that's just matrix multiplication for you there. Now, that's the wrong way, but now we are writing to the left here. So now we remember what we had at the top of the slide, the convergence here. So I just copied that down here. So if you let now your index k tend to infinity through a set B, any set in A, all right, then that will converge to the value of T of indicator function at UA evaluated at the point YB. And well, the upshot of all this is that if you look at this quantity here, all right, so you take MT red, apply it to the indicator function of A, and then you look at the sequence you get by letting K here run through a set B. Well, that sequence has to converge for all but countably many A and B in A. Let me just take note of that here, okay? So this says that if you have the reduced matrix of, it's the wrong way, sorry, okay, so if you have the reduced matrix of T, all right, and you apply it to this indicator function of a set A, and then you evaluate that at K, and you let K run through B, so this converges for all but countably many of our sets A and B in script A. All right. And the reason, okay, this is not, I mean, strictly speaking, I don't need this calculation, but this will sort of give you the intuition for what is to come next. And this is, I thought I should try and give you at least one calculation in detail, because if you never work with this, a lot of this is going to look very mysterious, because unsurprisingly, I mean, this is a technical proof, and there's no way I'm going to actually give you the details here. Even if I spent all 3 hours, I don't think I would have got through it. And certainly you would have fallen asleep for sure. Anyhow, so this is now the key reduction lemma, all right? So the way these proofs, I think, tend to go is that you start out with, well, you have your conclusion you want to reach. This is this few operator results. And now we want to say, if we had an almost disjoint family with that property, what should it satisfy, all right? So basically, we will show that if we have an almost disjoint family, which for every m in this set, the boldface M, remember they were essentially the matrices that represent weak star continuous operators on L infinity, if you like. Okay, so if you can find it, so for every m, one of the following 3 things holds, then we're done. Okay, so this is basically shifting this. This is a reduction lemma because it shifts the work from trying to work with operators to trying to construct an almost disjoint family with certain properties. So we're now basically shifting the problem into infinite combinatorics, if you like. All right. So the first condition that you can have for your given M is that there are uncountably many A in the set, script A, that will reject your given matrix M in the sense that this sequence here, okay, this diverges. And you will recognize that from my writing here. So this corresponds to taking A and B to be equal in this calculation. And you will immediately see that if I am in case 1, right, what I said here is that this sequence can diverge only for countably many A. So in other words, if it diverges for uncountably many, then certainly we kill the matrix M here, meaning that M cannot represent a bounded operator as, I mean, it can't be the reduced matrix of any operator T. All right. So, and this, as I say, this is the name of the game now. We are basically, I mean, it's a bit like a sort of fighting vampires or zombies or something. In my mind, the idea is that you have all these matrices in the set boldface M. Okay, we want to rule them out as candidates for reduced matrices of bounded operators in order to say that we have very few operators in this sense here. All right, and what do you need to do that? Well, you basically need to kill them off, but because they are like vampires or zombies, just killing them doesn't really work. It's not even enough to do it countably many times. You need to do it uncountably many times to be sure that the beasts are completely gone, right? And this is basically because of this. I mean, you can have countably many exceptions. That's the intuition that goes on here. Okay, so the second condition we have here is that there could be uncountably many sets A in the almost disjoint family A that will undermine M, in the sense that if you look just at the matrix M applied to the indicator function of a single point, so in other words, your unit vector basis of C0, if you like, okay, and then you let K run to infinity through A, then that will not converge to 0. That's another way to say that you can't be a credible reduced matrix. Or finally, if you can find a lambda, a scalar, and a countable subset A prime of A, such that when you stay away from that countable subset, so in other words, in this co-countable subset, A except A prime, that will admit the matrix M minus lambda I. So here I is just the identity matrix in this set here, the bulk is M, so the one that has ones on the diagonal and zeros elsewhere. Okay, so what does admission mean here? Well, it means that if you take M and you subtract lambda along the diagonal, and then you evaluate it at the indicator function of the set A, and you then take that the value at K, you let K go to infinity through another set B in here, okay, then that would tend to 0. All right, so basically what this says here, that condition, that should remind you of the calculation we did here, and this basically tells you that M is now a reduced matrix of some bounded operator, but that bounded operator is basically of the form lambda I plus something with set of a range. So of course, some matrices must represent operators because we can't kill all operators, right? There are some left, and that's what the third condition tells you. Okay, so they are the three conditions you're looking for, and there are some words associated with them. I just included them from the paper to perhaps help with a bit of intuition, but you don't need to remember them. If I ever need them again, I will mention it. But really, the key thing is just that you can do something like that, okay? So, as I say, what this reduction lemma does is it basically tells us now we're left, if you like, Banach space theory, operator theory, our comfort zone. We are now out into infinite combinatorics. We need to construct an almost disjoint uncountable family A satisfying the above clauses. I'm not sure whether that's good news or bad news, but it's how these proofs tend to go. So recall admission, that meant that if you apply M to your indicator function 1A, you evaluate it at K and let K tend to infinity through the set B, then this has to tend to 0. All right? There's a problem with that notion because it's not closed under finite unions or undertaking subsets. This has to do with the way that when you do matrix multiplication, this thing here is not well behaved, because when you take sort of the union, if you think of the indicator function of A union B and you apply the matrix to it, it's not enough to know how M behaves on the indicator function of 1A and 1B. There's also the bit where it says A except for B or B except for A that will play a role, and that can mess you up. So admission, although it's necessary, we need it in our reduction lemma, we need it, but actually it doesn't work very well in this construction, so we need to replace it with something else, which is a little bit technical to introduce, but it sort of is reminiscent of the idea of a compact operator. So let me just try and take you through this. Okay, so we have our infinite set A, we have one of these matrices M with elements M, K, N here. We fix a number J. Then we want to doctor our matrix here M, dependent on A and dependent on the index J. We've said we've chosen, all right. And how do we do it? Well, it's sort of a truncated matrix. We basically say MJA. Well, the KN entry is the same as from the original matrix if K and N are both in A and N is larger than J. So think, N is the column number, so we need to have the columns after J, and then we keep the entries from A, and well, everything else is discarded. Okay, so this is like a truncated matrix and also compressed to A. So if we accept that definition, well, then now we can say that this set A accepts the matrix M if the norms of these matrices here, so remember that was the soup of the absolute values of the row sums with absolute values, right? If that tends to 0. Okay, and what I'm saying here really, if you think of this in matrix, in operator language, which at least to me is much more, much easier to relate to, is that if you think of this matrix M representing an operator, say T from C0 into infinity, and what you've done is you compressed the matrix to the set A, and what you then get is a compact operator. And this is simply because, well, in the language of Banach algebras that I'm familiar with, the standard basis projections, they are a bounded right approximate identity. Or in other words, I mean, if you take a compact operator and you cut down from the right with the basis projection, then that converges to T, and this is because the zero basis is shrinking, right? So that's basically what this acceptance notion means in operator theory language, all right? And then there's a more general variant here. So we said what it means for a single set to accept the matrix M. Now, for a whole almost disjoint family, we say that it accepts M if the set A union B accepts M for every pair A and B in script A. And this is how we sort of feed in here the necessity to be well behaved under unions. That will be absolutely essential when we get to our construction later. Okay. So let's try and see how the proof now goes. Okay, so starting point, we pick an uncountable almost disjoint family, say script C, such that, well, if you look at the indicator functions of the sets in your almost disjoint family, right? An indicator function takes value 0, 1. So obviously you can think, I mean, this, wait, that's the wrong one, right? I wanted to point at this one up here. 1c here, right? That's a function from the natural numbers into 0, 1. All right. So it's naturally an element of the Cantor cube over there. There you have it, right? Okay, this is naturally an element. And now we want to have this collection here to be a Borel subset of the Cantor cube. This is the key. This is a key starting point that we use the Borel structure here. So in other words, the Cantor cube has extra structure because it's a compact space, right? But with a proper topology. Okay. Now we define a certain modified set of matrices, namely M prime, which are all those matrices where we can find a scalar lambda M, and we can find a countable subset of our given almost disjoint family, such that if you stay away from that countable subset, then that family will accept M minus lambda I. All right. So that was the notion of acceptance we had on the previous slide. All right. Well, if this set is everything, then I can skip a lot of stuff here and I can jump to the next slide. I kind of suspect that that cannot actually happen, but just to, it's quicker to say, just to move on if it did happen. But if it doesn't, then we enumerate the complement of M prime. So to some extent, the complement of M prime is the awkward part, okay? If we were lucky M prime was everything, then the whole thing would be dead easy. And the problem is to try and get to a situation where it is. So now we enumerate the complement in the following way. So we enumerate it as M psi, where psi is any ordinal less than a continuum. And how can we make sure there are so many matrices? Well, each of them we actually repeat continuum many times. Okay, so I think in a general situation, I mean M here, of course, this remember consists of N by N matrices, N being the natural numbers, right? So there are indeed continuum many of those. All right, but you can repeat each of them continuum many times, and there's still continuum many of them. That's how ordinal or cardinal arithmetic works, right? And well, now we have this enumeration. So what else can you do than a transfinite recursion, right? So that's how these things tend to work. I mean, I'm quite intrigued by this because I think it might be the first time in my mathematical career that I actually used transfinite recursion for anything other than sitting exams as an undergraduate, right? It's not, I mean, usually I think in functional analysis, we tend to use Zorn's lemma rather than transfinite recursion. But once you move into this area, I realize then doing actual transfinite recursion is a much more commonplace thing to do. Okay. Anyhow, so let's see. What shall we do? We do our transfinite recursion on the ordinal psi, all right? And so we choose two sets B psi and C psi in our almost disjoint family script C with the property that when you take the union of the two guys, then you can find inside that union an infinite subset that rejects M psi. Don't worry what that exactly means from the previous slide. Just remember that this is what it does, and then we will see the reduction lemma later, and we will check that in a certain situation, then we have condition 1 satisfied in that reduction lemma, no matter what rejection really meant. All right. And the second thing we need is that these pairs are disjoint. Okay. So let me just try and unpack the precise statement here. It's okay that V psi and C psi, they could be the same thing, right? So one of these sets could be a singleton, but basically, because we are doing recursion, right, we think we've constructed all these guys now, and we're trying to pick those guys. And when we are picking these guys here, we have to stay away from all the previous ones we've chosen. And this is a point where you need to make sure you have enough room to do that. You don't run out of space or paint yourself into a corner. The reason we can do that is essentially a classical theorem of Alexandrov and Hausdorff. So they proved that every uncountable Borel subset of the Cantor cube is in fact cardinalis C. So I believe this work was done in the happy old days when people still believed that the continuum hypothesis ought to be a theorem of ZFC, and they were basically trying to establish in more and more cases that the continuum hypothesis is true. And so in particular what Alexandrov and Hausdorff showed was that if you restrict attention to uncountable Borel subsets of the Cantor cube, well, then the continuum hypothesis is true. Once you're uncountable, you are immediately of cardinality C. Okay, so now, so this is basically, this is what guarantees that we will never run out of space, that there will always be a room to make this. I mean, I'm brushing a lot of stuff under the carpet here, I should admit, but this is the, sort of the gist of it, right? And now I can tell you what my almost disjoint family is, because it's basically the collection of these sets xi chosen up there. And note that because B psi and C psi belong to this almost disjoint family C, and these pairs are distinct, then clearly the sets xi are also going to be disjoint, almost disjoint. Okay, so this is certainly an almost disjoint family. All right. And well, now all that remains is to check that every matrix M satisfies one of the three conditions from the reduction lemma with respect to that choice of A. And so that's what comes on the next slide. But let me just remind you of what the reduction lemma said. So basically, I want the three conditions are either for my given M, there must be uncountably many sets that reject it, or there must be uncountably many sets that undermine it, or there must be a scalar lambda and a countable set A prime, so that if you stay away from A prime, then the this co-countable almost disjoint family admits in minus lambda I. And as I say, the wonderful thing now is you don't need to remember what reject, undermine, and admit means. We just need to know that certain things happen, and then we can kind of keep going. Of course, in the proof, it is important, but they are not details I'm going to dwell on here. All right. So let's see why this is true. Okay. So, well, the complement of M prime was this enumeration of the matrices M psi, with each matrix appearing many times, and script A was the sets A psi, where A psi was chosen in such a way that it rejects M psi. All right, so let's now check the possible cases. Okay, first, if M is in this set here, right, then we set ourselves up for a winner, right? Because then M obviously is equal to M psi, but because each matrix here is repeated continuum many times, M appears continuum many times for continuum many distinct psi, all right? And every matrix every set, A psi rejects M, right? So in other words, there are continuum many psi here where A psi rejects M, and therefore one is trivially satisfied. Okay, so we basically, as I say, everything is set up to fit with that one to make that case dead easy. Okay, the second case that is also dead easy is if the set A prime of all the sets A in our almost disjoint family that undermine M, whatever that means, if that set is uncountable, then the second condition is satisfied. Again, that's just, that is just trivial. So basically what remains now is to consider the situation when M belongs to the set M prime, and this family is countable. All right, so that's what will happen now. All right, that's basically, I mean, this is sort of it's like a salami technique proof, right? We slice it off, we do some easy cases, and then we are left with a hard case in the end. And this is now what we're going to do. So let me just remind you what it means that M belongs to M prime, or slight summary of that, okay? So the condition that M is in this set M prime, well, that means that there is a countable subfamily C sub M of script C, the almost disjoint family we started with, all right? And there is a scalar, that one here, yeah, lambda M, such that if I look at this truncated almost disjoint family, so the co-countable family there, it will accept the matrix M minus lambda M times the identity. So in other words, I take my matrix M, I subtract lambda M along the diagonal, and the family there accepts it, okay? Then the other thing I need to remember now is that when I chose A in this set script A, it was contained in the union of some B and C coming from the family script C. Before, when I chose it, it was in my recursive construction, so there were subscripts psi on them, but that doesn't matter for us anymore, all right? But what matters is that because this family here, Cm, is countable, well, of course, and these sets here, B and C, they were distinct, the pairs, right? So in other words, I can have B is in Cm or C is in Cm only for countably many of the sets A, because otherwise I run out of space there, all right? And now comes the key point where I need that the new notion we introduced of acceptance, that passes to subsets of finite unions. That was a problem we had with admittance, it didn't, but acceptance does, all right? So in other words, I can now say that if I stay away from a countable subfamily, say A double prime, then the rest here, A, except for A double prime, will accept the matrix M minus lambda I, all right? And, well, note also that no A outside of A prime will undermine M minus lambda I. Why is that? Well, the formal definition, now we need to remember what it means to undermine. Well, basically, to undermine means that this sequence does not converge to zero when I let K tend to infinity through A. All right, that was the definition of undermine. To undermine is that this sequence here does not converge to zero when K tends to infinity in A. All right, so I need to show that doesn't happen, or in other words, it does converge to zero here. Why is that? Well, you simply do your matrix, usual matrix calculation here, right? How do you evaluate this? Well, you take M of the singleton set in here at K, and then you subtract, well, lambda, and then you apply the identity to this one. That doesn't change anything, and you evaluate that at K. But of course, now we know that this one is 0, except at one point, so that is trivially 0. And the first bit here, that tends to 0 because because of my choice of A prime, right? I'm in the set, right? A prime, that was a collection of A that undermined M. So as long as A does not undermine M, then I know that this guy also tends to 0. Okay, so the upshot of this is that I have concluded two things. First of all, if I stay away from A double prime, then this almost disjoint family here accepts M minus lambda I. So and if I make the set I take away larger, that the acceptance will still happen. Also, I have shown that, again, if I stay away from A except for a single prime here, then no element in there will undermine m minus lambda I. So in particular, if I remove even more sets, that will still be true, all right? And the key thing is now I have the same co-countable subfamily of A here, all right? And then it's a little lemma to show that if you have a family that accepts a certain matrix and no element of it undermines it, then you can show that that implies admission. I accept this is a linear where you need to look at the definitions and work with it. It's not that difficult, but of course, I mean, there's some technical detail I'm brushing under the carpet there. But now the upshot is I produced a co-countable subfamily of A, which will admit this guy here. And that's precisely what the third condition in the reduction lemma said. And that's pretty much taken me to the end of this outline of the proof. Okay. So I think we should take a deep breath here. I accept this was somewhat a technical bit, but any questions?
Yes. So if I'm not wrong, your construction means that the KA is cardinality continuum, right?
Pardon?
Your compact space KA is cardinality continuum.
Yes, yes, definitely.
So even your any continuum hypothesis assumption, and your argument cannot produce a C of K where K is cardinality less than continuum.
No, I don't think so, because
you need this Borel assumption.
Yes, absolutely, yes. But also, if you remember, we had one of the results I mentioned yesterday, and I now have to look around which of the authors are here. Are you one of them?
No,
the fact that, or is it you, Jesus, and Alberto, and maybe Gregorz and Felix and Martichevsky? Is that right? You've shown that if your family A has cardinality, uncountable cardinalities, but strictly less than C.
Yeah,
then there is only one. There's only one basically CK space you can get, and that is in particular isomorphic to its square.
Yeah.
So you can never hope to get this kind of result. I think you need some extra axioms like Martin's axiom and the negation of the continuum hypothesis. But here we just work in ZFC, so this can't happen. Okay, but that's, I mean, it's a good thing to wonder, right? But basically, I mean, as far as I understand those results of those aforementioned people, right? The idea is that if you have, if you believe the continuum hypothesis is false, right? Then for each of the intermediate values between omega-1 and the continuum, you essentially only have one interesting choice of an almost disjoint family, because whatever you choose, different ones you might choose, you get the same CK space. Up to the continuum, then you have 2 to the C many, so then it sort of totally explodes. Okay, other questions? Yes.
So if I remember correctly, I think you said that the reduced metrics kind of represents loses some information.
Yes. Yes.
Why doesn't it encode everything?
Well, because I mean, you don't. You don't keep the information at the points, these points YA.
Not even with the continuity and density.
Well, but no. I mean, the problem is that we don't have. I mean, I don't think we have the right kind of a continuity and convergence here. This is the thing. This is it's just more like a shadow of what we're doing, because we're basically. I mean, we're reducing it to the norm we put on M, right? It's not the operator norm coming from space. Right, the norm on M is essentially the norm that you get by regarding M as an operator from C0 into an infinity. So we kind of lose some information there, but somehow, I mean, the miracle is that it retains enough information that we can still do stuff with it. Okay. Other questions? Okay, well, I can offer 2 questions from the paper. So one that is firmly within the infinite combinatorics domain, namely the construction we give doesn't give a maximal almost disjoint family. So a maximal almost disjoint family is what you would imagine, namely one where you cannot find any single infinite subset of the natural numbers that you can add to it without it no longer being almost disjoint. Okay, so you can't enlarge it any further. Okay, the almost disjoint family we get is not maximal, but the question is, could you find one where that would happen? All right. The second question is much closer to my heart, namely, if you look, I mean, so the construction we give gets you this quotient algebra to be one-dimensional. All right. So an actual question is to wonder what other quotient algebras could you realize in that fashion. So in other words, I mean, here, as I say, when you talk about few operators in this sense, it doesn't make sense to try and take the quotient modulo the compacts or something, because you all immediately get copies of the zero and so on. So that's too much. But if you kill off that bit, so to take the quotient modulo the operators with separable range, what other quotient algebras could you potentially go to find? All right. So basically, if you were to make progress on that, right, you would have to sort of like play around with these ideas of admission and undermining and acceptance and whatnot, and try and see which reduced matrices should you now allow in addition to the ones you had before in order for that to happen. And basically, our thinking behind this is that this should be the counterpart from Rovka spaces of what I now consider a rather famous open problem, namely to determine which unital Banach algebras you can realize as the Colkin algebra of some Banach space X. Right? So there's a considerable literature nowadays, I mean, following the Agilus-Hayden construction, there's a considerable literature of Banach algebras that you can realize in such quotients. As far as I know, there's still no example known of a Banach algebra that you cannot realize in that way. I should perhaps say that up here you have a natural restriction, because you cannot exceed density C continuum, because basically that's the density of that beast there. So that you cannot get any larger than that. But that's the only restriction we know at the moment. Okay, so let's just take a little break here after these questions and digest all this. And then now I'm going to change direction a bit and hopefully do something that is a little bit lighter. Okay. So I appreciate that this is a bit perhaps off topic in a conference on Banach spaces and Banach lattices, but I will get firmly into the realm of Banach spaces shortly. But I should apologize to the people who do Banach lattices, because of course to you a homomorphism is obviously a lattice homomorphism, but I'm now going to talk about algebra homomorphisms, and to not have very long sentences. All my homomorphisms from now on will be algebra homomorphisms. All right. And well, the connection to the paper with Piotr is that we showed that if you have such an almost disjoint family where B of C0 Ka admits few operators, then every homomorphism from this Banach algebra here into any Banach algebra is automatically continuous. All right. And in fact, we showed a slightly stronger result than that. And well, this was an immediate corollary, because we showed without the assumption here of your almost disjoint family having only few operators, but if you take any almost disjoint family, then if you take a homomorphism from now the ideal of operators with separable range into a Banach algebra, then that is automatically continuous. Okay, and I'll tell you in a minute why this is interesting, but let me just point out that once you then know in this case that your homomorphism is continuous on this one, then it follows automatically that you can extend by one dimension that you must still be continuous. All right. But the question, again, I could add to my list on the previous slide, that this leads to is whether one can find an uncountable almost disjoint family A such that B of C0 Ka admits a discontinuous homomorphism into a Banach algebra. I think this is quite an interesting question, and the people who believe that there are enough uncountable almost disjoint families out there to prove almost anything, I'd like to challenge them to try and see if they can solve this question. I'd be very interested to hear if anyone had any suggestions about that, because I think this is perhaps, I mean, I think this might well be a doable problem, unlike some other problems people mention. I don't think a lot of people would have thought about this. So if one knows enough about how to construct uncountable almost disjoint families, I think there might well be a good chance of having a go at this problem. Okay. And I should like to advertise for the non-experts here that automatic continuity of homomorphisms, or the lack thereof, is one of the oldest lines of research in the theory of Banach algebras, so that has motivated a lot of the research that has been done in the theory of Banach algebras. And actually, I mean, when I started out my career far too many years ago, it looked like this area had sort of almost come to a standstill, and people have done as much as they could in that area. So I'm rather excited that in more recent years, because of the emergence of new exotic types of Banach spaces, actually there are new results we can prove, such as this one up there. And let me just try to explain, so to go back to the origins here and explain to you why that's even a theorem. Okay, why would you wonder why isn't this just a result you can take off the shelf? Well, this is due to the seminal automatic continuity result for Banach algebras of the form B of X for a Banach space X, and this is due to Barry Johnson. And you will observe I usually don't give initials in my accreditations here, but for Barry Johnson, I thought that was significant because I think if you say Johnson in this context, everyone would credit Bill Johnson for it. But Barry Johnson, of course, was a major figure on the functional analysis scene in the UK from the 1960s until he sadly passed away in the early 2000s, far too early. But he was sort of one of the leading figures in functional analysis in the UK for many years. And what Barry proved in the late 60s is that if you have a Banach space, which is isomorphic to its square, then every homomorphism from B of X into a Banach algebra is automatically continuous. And of course, in those days, I mean, in 1967, Banach space theory is, well, at the risk of offending some people, I would say they were still in the relatively optimistic state where many counterexamples had not been discovered. I mean, there was still hope all separable Banach spaces have the AP, or basis even, right? And that Shelton space didn't exist, let alone Gauss-Moret or Jules-Hayden or whatever, right? So people probably thought that many things could be true, and in particular, most Banach spaces known at the time were isomorphic to their square. In fact, I mean, you can weaken this hypothesis slightly, but I don't want to go into the technicalities of that. But also, so I mean, later on, actually, some Banach spaces which are not isomorphic to their square or satisfy any of the weakened versions of it have been shown again that the same conclusion will hold. So all homomorphisms with B of X are continuous. So if you take James's quasi-reflexive space, even the Peath variant of it, then George Willis, who was a student of Johnson, in fact, he showed that again, all homomorphisms are automatically continuous. Katie Ogden, student of Garth Dales, showed around the same time that if you take the continuous functions on the ordinal interval up to omega-1, then again, all homomorphisms are automatically continuous. In fact, I think Katie did slightly more in her PhD thesis. I think she looked at some other uncountable ordinals as well. I forget whether they had to be so something around co-finality or whatever. I forget the specifics, but for a lot of uncountable ordinals, in fact, she solved it there. But in this particular case, there's a much simplified proof in a paper by Tomek and Piotr and myself from 2014. But these, I mean, at the time, I believe at the time when Johnson proved his original results up here, these were probably the only two examples known of Banach spaces not isomorphic to their square. Right, this one, the James space, this is an observation of Polchinski, and the continuous functions up to omega-1, that was the result of Simeteni, that is not isomorphic to a square, and they basically, I think they appeared like in the same volume of the bulletin of the Polish Academy or something like that, around 1960. Okay, so in other words, I would conjecture, even though I don't know this for sure, but I would conjecture that at the time when Barry Johnson proved this result, he might well have thought that it might be true for all Banach spaces. Okay, but it's not so, as I shall explain to you shortly. But let me raise another question that when I was preparing this talk, I realized that I think this is slightly strange. We don't know the answer to that. Okay, so suppose X is the Jules-Hayden space or the Gauss-Moret space or something like that. Do we know in those cases that every homomorphism of B of X into a Banach algebra is continuous? Really, I mean, the techniques that are used both to prove these results and also the result I mentioned on the previous page, I mean, they very much build on the techniques that Johnson developed for his original proof about sort of splitting a space into direct sums of copies of infinite like isomorphic copies of certain subspaces. That's sort of, you do this sort of construction, and there's a standard scheme you go through, and this is basically what these proofs utilize. And I don't think you can do anything like that for these in these cases. So I think that would be an interesting question as well. Okay, well, it's not true that all homomorphisms from P of X are automatically continuous, but within ZFZ, that's actually a very hard problem to solve. Well, the most important example of a Banach space X, where you have a discontinuous homomorphism, is a Banach space that Charles Reid constructed. And I know for most people here, if I say Charles Reid and then constructing a Banach space, you will think of something with without invariant subspaces. This is a different Banach space than those. So this was a space that Charles constructed in the late 1980s, and it admits so-called discontinuous point derivation. I'm not going to tell you what that is, but instead I'll give you a stronger property, and that I hope will be of slightly more interest and relevance to people in Banach space theory, because it actually says something quite powerful about the structure of this Banach algebra here. All right. So let little L2 straddle the unitization of the Hilbert space L2 endowed with the trivial product. Okay, what does that mean in practical terms? Well, you take your little L2, all right, you add a formal identity to it, all right, so I write that formal identity just as the number 1 times a scalar field, all right. So now I need to norm that vector space here. Well, I just take the L1 norm, so I take for X from L2, I take the usual Hilbert space norm, and I take the absolute value of my scalar S, all right. And now I want so I want to endow this part of L2 with the trivial product. Trivial product just means all products are 0, and I want this guy to act as an identity. So if I have 2 elements, so X plus S1 and Y plus T1, all right, and I want to multiply them together, well, I just multiply out the brackets and see what I get, right? I declared X times Y is 0. I declared 1 times 1 is 1. So that gives me, there's nothing here. And then, of course, I get 1 times Y is just Y, so that gives me SY, and 1 times X is again X, so that gives me T times X. So that's what I mean by the unitization of the Hilbert space L2 endowed with the trivial product. All right, and then the result that you can actually get that makes various things work much better for Reid's space, and I think it kind of summarizes the key idea in the construction Reid gave, is that you can find a continuous surjective homomorphism from all the operators on Reid's space onto this kind of Hilbert space with trivial product, and then with the identity, formal identity adjoint. Obviously, you need this guy to be unital if you have a surjection here, right? Because you need to send the identity operator to an identity element here, right? Okay, so you have such a continuous surjective homomorphism. Its kernel is just all the weakly compact operators, and this extension here, where you take the ideal of weakly compact operators, you put them inside all the operators, and then you take the quotient map psi onto L2 triple. Well, that splits in the category of Banach algebras. So that means that you have a right inverse of psi, so a map that goes back here, and that is a continuous algebra homomorphism as well. All right. And once you have this, you can do all sorts of wonderful things, because in particular, because you have the 0 product here, except for that extra identity. Well, L2 with a 0 product, well, L2 is an infinite dimensional Banach space, so it has lots of discontinuous functionals on it. All right, and of course, when you have 0 product, then discontinuous functional is also a homomorphism, right? So that means that then you just extend the map 1 to 1, and then you get lots of discontinuous homomorphisms in that space. All right, so that's basically how you can get discontinuous homomorphisms, lots of them out of this example. But I conjecture that there will be lots of other interesting examples along these lines and applications of this Reid Banach space. I think there haven't been enough use made of it. So the reason why this result came up, this was with my former student, Richard Skillicorn. We needed it. We were looking at extensions of Banach algebras of the form B of X, and we wanted to prove something about them. And we found that Reid's space was exactly the thing we needed for it. This was the tool we needed. Then we did some sort of abstract constructions with it to solve some problems. But I'm not going to say more about that, but I just wanted to mention that Banach space as something that I think could have more use also in Banach space theory. Okay, let me continue with more examples of discontinuous homomorphisms from B of X, but now I need to assume the continuum hypothesis. And why is that? Well, basically because it's a very famous result of Garth Dales and Jean Estelle independently in the late 1970s. So they solved, I think, what was known as Hablansky's conjecture. So what they showed was that if you have any infinite compact Hausdorff space K, then C of K, now taken as a Banach algebra, admits a discontinuous homomorphism into a Banach algebra. And I think it's fair to say that at the time when Garth and Jean proved their results, well, individually, I mean, they were working independently, and each individually was surprised they needed the continuum hypothesis to make this work. They thought, at least I know Garth thought, he was just not, say, smart enough to avoid that. Okay, I don't know about Jean, but the fact they both came out with it presumably gave a little bit of a hint that maybe it was necessary. And in fact, it turns out that there is another model of set theory in which all homomorphisms from C of K into a Banach algebra are automatically continuous. So that was a result of Hugh Wooding that came out shortly after. In fact, I think Hugh Wooding at the time was still an undergraduate at Stanford or something. So that was rather amazing. He managed to solve that. But that's a different story. The upshot here is that if you have C of K as an algebra quotient and you assume the continuum hypothesis, then you also get discontinuous homomorphisms from the algebra that the quotient came from. So that's what I want to use here, right? In other words, if I have a Banach space X that such as B of X admits a continuous surjective homomorphism of C of K for some infinite compact Hausdorff space K, then you can simply apply the open mapping theorem and lift your discontinuous homomorphism up to all of B of X, and it will still be discontinuous. Okay, so that kind of changes the perspective a bit. Now, if we can find Banach spaces X, where B of X admits C of K as an algebra quotient, then we will get discontinuous homomorphisms. And such examples are known. So in particular, you can get L infinity as a quotient here. There are two known constructions. I think the first is due to Mankiewicz. He even got a super reflexive Banach space with that property. The other construction I know of is due to Dales, Loy, Willis. They did a much more hands-on construction. In fact, they glued together some quasi-reflexive James spaces with different indices, and they wanted to prove some other automatic continuity result. So they needed something that was kind of more concrete to work with. Also, much more recently, in the context of what Banach algebras can be Kolkhin algebras, Motakis, Puglisi, and Sisimopoulou showed in 2016 that if you take any countably infinite compact metric space K, then you can find a Banach space X for which there is a continuous surjective homomorphism of B of X onto C of K. And as I say, not only that, they actually realize C of K as a Kolkhin algebra, so the kernel of your phi is the compact operators. All right. And much more recently, I think last autumn, Pavlos Motakis announced that he's managed to do a similar construction here, but now he doesn't need the compact metric space to be countably infinite. All right, and note here that because we are looking at C of K as not just a Banach space, but a Banach algebra, there are now lots of different isomorphism types of C of K for K and uncountable compact metric space. We don't have Milutyn's theorem, in other words. I think actually, now that I look at my slide, I think there might be another example you can add there, because if you take ours as space with an unconditional basis that's not isomorphic to its hyperplanes, I think you get L infinity mod C0 as an algebra quotient of that. And of course, that's just the continuous functions on the Stone-Check remainder. So again, from there, you will also have discontinuous homomorphism, and there are probably other examples I've forgotten. But basically, if you assume the continuum hypothesis, you can give quite a few examples. Here's another one, the one I called the first Krushmida CK space with few operators. So remember, that was the one where every operator on your on C of K is a multiplication operator, also a weakly compact operator, or a strictly singular operator if you prefer. And again, I want to advertise a particular property of this space because I think that might be helpful if people want to work further with it, because B of C of K actually has C of K here as an algebraic quotient. Simply, if you take the quotient modulo the weakly compacts, and if you arrange that K doesn't have any isolated points, which you can, then in fact, again, you get this split exact sequence in the category of Banach algebras. So that means if you take your map phi from B of C of K onto C of K, it has a right inverse, which is again a continuous algebra homomorphism. And that means, so in other words, people would say that B of C of K here is what's called a semi-direct product of the weakly compact operators and C of K. So that gives you a lot of opportunity to analyze B of C of K in more detail there. All right. But just to come back to the question I asked earlier about discontinuous homomorphisms from B of C naught or Ka on almost disjoint family A. In fact, I don't even think I know any example within ZFC, so without assuming the continuum hypothesis, where B of C of K admits a discontinuous homomorphism into a Banach algebra. So for people interested in C of K spaces, that's another good question, I think. I'm not sure that many people would have attempted something like that. Okay, so let me invite some questions here. If anyone has any questions. Yes?
So could you show again Charles Reed's example? Maybe?
Yes, certainly.
Okay, thank you. So how can you say again maybe exactly how does it follow that you have discontinuous homomorphisms? Is it because on L2 tildes there are such or what?
Yes. I mean the idea. Okay, so the general scheme is that if you have an algebraic quotient, and when I say algebraic quotient, it should be a continuous algebraic homomorphism quotient, right? If you have an algebraic quotient that admits a discontinuous homomorphism, then you just compose it with a quotient map, and that will still be discontinuous by the open mapping theorem. Okay, so in other words, the key thing is that to get the discontinuous homomorphism here, we just need to find one here. But because we have the zero product, that's essentially the same as finding discontinuous operators. And once you're infinite dimensional, that of course is dead easy, right? I mean, there's no such question as uniqueness of norm for Banach spaces because, well, that only happens in finite dimensions. Whereas my next topic actually is about the connection between discontinuous homomorphisms and uniqueness of norm. And you will see, I mean, that's somehow the connection between these topics. Okay?
Okay, thank you.
Other questions? Yes.
So here the choice of L2 is just because it's possible to build this homomorphism.
Pardon?
The choice of L2 is because of the construction of the homomorphism, because for the
Yes. Well, the L2 here comes out of, I mean, Charles Reed's construction. I mean, this Reed space, in some way, I mean, this is it's a very interesting example because, in some sense, you could tell students after our first course in Banach space theory what it is. You don't need anything fancy. You don't need like Silson or Gauss-Moret or something crazy like that. You totally need to know what the second dual of a Banach space is and how to do quotients and maybe a bit of weak topology or something like that. But that's it. I mean, it's very elementary in that respect. But at the same time, it's extremely ingenious because what he does is he takes some, if I remember correctly, he takes some sort of family of Banach spaces with a symmetric basis, but ensuring that the symmetric bases behave in very different ways. And then he repeats them over and over again, and he sort of puts in maps that links them back into themselves. So it's a sort of based on the idea of the James space, the way he glues it together, but the way he glues it together, if I remember correctly, is kind of in a way, so you get this L2 out as a quotient. But as I say, I strongly recommend people look at the paper, or if you want perhaps a, I mean, when Richard, I mean, if you look at Richard's PhD thesis in particular, I think he did quite a nice survey of it, because I will say, well, Charles's paper, now one shouldn't speak ill of the dead, but I think it's fair to say that the paper was written pre-LaTeX. That was when you wrote a manuscript by hand, you gave it to a secretary who typeset it and submitted it to a journal. That meant there were typos in the manuscript. And this manuscript definitely has a fair share of typos that can make it slightly hard to follow at times. So once you sort of overcome some of those and you work out what it really should say, then it's a beautifully simple construction. And this is why, as I say, I also wanted to mention it, because it is really quite a nice example. Okay, other questions? And as I say, I conjecture that should have other applications in Banach space theory. Okay, so as I just said, now I want to talk about uniqueness algebra norm, and that's actually closely related to automatic continuity homomorphisms, and I hope I will get to say that. Okay, so basically the aim here is for given Banach space X to decide whether every quotient algebra of B of X by one of its closed ideals has a unique algebra norm. Okay. And the main result that links it to my main topic here, work I'm currently doing with Max, and which says that if you have this almost disjoint uncountable family that admits a few operators, then every quotient of B of C naught Ka by its closed ideals has a unique algebra norm. And you will, I mean, a key ingredient I can reveal to you, I don't think I'll get to the proof of this, but the key ingredient in the proof is obviously that we know there are only 4 closed ideals. So there's a finite number of checks we need to carry out, okay? But let me just start again at the beginning, because I appreciate this might not be sort of mainstream topic here. So submultiplicative norm is what I call an algebra norm. So it just means that the norm of the product is the product of the norms. And we say that an algebra B has a unique algebra norm up to equivalence, if we want to be careful. If whenever you take 2 algebra norms in this sense on B, well, then they are equivalent in the usual sense that they are constants, such that one dominates the other, both ways one. Okay. And I should perhaps say that I'm doing something slightly dodgy here, because usually if you work in a unital algebra, you'll also require that the multiplicative identity has norm 1. But it will be simpler in a little while if I ignore that convention, and it's not a problem, because if you have a unital algebra with where the identity doesn't have norm 1, then you can always renorm it in an equivalent way to get that condition satisfied. So it's not a major problem, it just makes certain things a little bit more technical. So that's the uniqueness of norm condition. A much more common study is to ask whether B has a unique complete norm, in other words, a unique Banach algebra norm. And of course, by the Banach isomorphism theorem, in that case, it would suffice to establish that one of the 2 complete norms dominates the other. Then, as I say, you fire Banach's isomorphism theorem on it, and you get that they are immediately equivalent. But if you drop completeness, then you need to do the 2 inequalities there separately. And that's what we should do. And let's just start with the right-hand one. So that's the one we call maximality of the algebra norm. So maximality simply is that if you take any other algebra norm, say triple bar here, then up to a constant is dominated by the given norm. And we can write down some conditions that are equivalent to maximality. So indeed, the norm is maximal precisely if every homomorphism from B of X into a from B into a Banach algebra is continuous. So that's a connection with the previous topic. All right, and that's the same as saying for every closed ideal of B, the quotient norm on B mod I is maximal. And that again is the same as saying that for every closed ideal, every homomorphism from the quotient into a Banach algebra is continuous. And let me just try and see if I can outline the proof of this. So there's the proposition. We want to go from A to B. And the idea is that if you know your norm is maximal, then we define a new norm for a given algebra homomorphism. What do? Well, we just take the maximum of the norm of the element A and the image in C here, our codomain of phi, the image of A there. And then because phi is multiplicative, you can check that gives you an algebra norm. then by hypothesis, of course, the new norm is dominated by the old norm up to a constant, and then we say, well, the new norm dominates the norm of phi of A, so Bob your uncle, right, you have phi is continuous. On the other hand, if we want to go back, we take a algebra norm on B, say triple bar, we complete B with respect to it, and then we just look at the formal identity map from B into this new completion. Well, then we say that's automatically continuous, and that gives us that the norm on B has to dominate the norm on C up to a constant. Well, C and D are clearly equivalent for the same reason, because you just fix your closed ideal, and then you apply the same reasoning that I gave to show that A and B are equivalent, all right? And B implies B, well, that was the result I just explained to Timur before. That's basically the open mapping theorem, that if you have a discontinuous homomorphism on the ideal, you can basically use the quotient homomorphism, and that will lift it to a discontinuous homomorphism on the whole algebra. And going the other way is, of course, clear, because we can do this for every closed ideal. So in particular, you can just take the zero ideal. Okay, so that was just a brief outline of how to connect these two topics. So the other part of the inequality is minimality of the norm. So that basically tells you the other bit that you say the norm is minimal if every other algebra norm dominates it again after a constant. And the result here is very similar, that the norm is minimal precisely if every injective homomorphism B into a Banach algebra is bounded below, all right? So just to see, well, we do essentially the same thing as we did before. We now define our new norm triple bar just as the norm of the image of the element, because we have injectivity. Of course, this will give you a norm, not just a semi-norm. Then you check as an algebra norm. Then therefore it must dominate the given norm, and that of course is the same as saying that if you move 1 over C over to the other side, right, that phi is bounded below by 1 over C. And to go the other way, we do the same thing as before. We take the formal inclusion map and we complete. Okay, so the consequence of this is that we can we get the following characterization of when every quotient algebra of B by one of its closed ideals has a unique algebra norm. Well, it simply means that every homomorphism from B into a Banach algebra is both continuous and has closed range. And so you can say this is sort of curious that this is about all quotient algebras of B, all right? This is only about homomorphism of B itself. Okay, so that's why I think this is a natural question to study when all quotient algebras of B by its closed ideals have a unique algebra norm. Okay, so let's see, any questions here? If not, I will just move on and see if I can give you a few of the background results at least before I finish. So Jude showed in the very early days of the topic, I say this is very, very classic Banach algebra theory. So he showed that the operator norm on B of X is minimal for every Banach space X. And well, as a corollary, of course, we see that if that B of X will have a unique algebra norm precisely if every homomorphism from B of X into a Banach algebra is continuous, right? Because the norm is automatically minimal, and this was equivalent to maximality of the norm. All right, and usually this condition will be satisfied. I mean, we cannot get anywhere if we don't know our homomorphisms of B of X are automatically continuous, or then we know immediately that there are discontinuous homomorphisms. Well, if you have discontinuous homomorphisms, you have inequivalent algebra norms, and usually by the examples I'm going to look at, we'll have this condition here from Johnson's theorem satisfied that they are isomorphic to the squares. So homomorphisms are continuous, or say in the case of the other space I was thinking of, this Rovka space, there again we had the theorem separately that homomorphisms are continuous. So the classical theorem about Banach spaces in this area is due to Mayer from 1992 in the bulletin of the LMS. He showed that for the classical sequence spaces, C0 and the little P, the Colkin algebra has a unique algebra norm. Okay, and of course, because the ideal of compact operators is the only non-trivial closed ideal in these cases, it follows actually that every quotient algebra of B of X by a closed ideal has a unique algebra norm, or in other words, that not only are homomorphisms here automatically continuous, they also necessarily have a closed range. And a generalization, a substantial generalization of that was done by Griff Ware in his PhD thesis, Australian National University 2014. So sadly, I don't think it has ever been published, but there was actually some good work in it. So Griff generalized this to the uncountable sequence spaces showing all the quotient algebras there will have a unique algebra norm. And the key ingredient he had for that was the fact that Matt Dawes had already classified all the closed ideals of B of X in those cases. And I think this appeared also briefly in Tomek's talk on Monday. So you have this sort of well-ordered chain of what is called kappa compact operators, although you can, I mean, so the result here with the kappa compact operators, I'm not going to tell you in the time what that is, but it generalizes an older result of Ramsch and Luft from the 1960s in the Hilbert space case. But I'd also like to advertise that there is more information or a different proof of this with a different description of these ideals in this paper I mentioned at the beginning by Johnson, Kanya, Shechtman, and also by Benzer Robart and Tomek from last year. Right. So let's see. So the main focus of where thesis was not actually about when all quotients of B of X mod a closed ideal has a unique algebra norm, but that was about the Qualkian algebra. And let me just briefly mention some of the cases that Griff covered. So this was the direct sum of finitely many LP spaces, or you can also take C0 to be one of the summands. He looked at, say, the C0 sum of little LP n for any p, or the also the LQ sum of little LP n's for any q. Well, now q has to be finite. We can't do an infinity there. He showed it for the the pth quasi-reflexive James space. He showed it for the Silson space, and probably quite a few others. But this is just to give you some flavor. As I say, there's a lot of good stuff in that thesis. The first example of a Banach space where the quotient norm of the Qualkian algebra is not minimal was given by Astala and Tully, and later Tully by himself also found such examples. But the thing that really got Max and myself interested in this topic is a paper that Bill Johnson spoke about in the Banach Spaces webinar early 2021, I think. So some ongoing work he's doing with Chris Phillips and Gideon Shechtman. So they looked at the capital LP spaces in the reflexive range. They showed that the Qualkian algebra there has a unique algebra norm. Of course, for p equals to 2, that's already known. So the main interest are the other p's. And in fact, they show that even for every complemented subspace of capital LP. But on the other hand, if you stay away from the Hilbertian case, they show that B of capital LP actually contains a closed ideal where the quotient norm is not a minimal norm. Obviously, all these norms, I mean, because capital P is a square Banach space, it has an overture square, right? So Johnson's theorem tells you that you have automatic continuity of homomorphisms. So you have always maximality of your norms. So the question is always about minimality. Okay, let's see. Okay, and maybe I'll just mention a very neat result here that is both in the work of Mayer and I think also in this Johnson Phillips Shechtman result. And then I will stop there. So basically, the idea is if you have already a maximal algebra norm, which you usually do by this automatic continuity relation, and if you know there is a constant k, so that whenever you take a norm one element in B, you can sandwich it between two other elements A and C with uniform control over the norm, such that what you get out of it is a non-zero idempotent. Well, then your norm is also minimal, and therefore you have a unique algebra. So what I want to say here is that a lot of the work when you're actually trying to prove uniqueness of algebra norm, it's about a norm-controlled factorization of idempotents through operators. So it's like you need to prove quantitative versions of often known results about known factorization results, but now you need to have this extra condition that you need to control the norm of the factorization. And if I had more time, I would have shown you a little bit more about that in the context of COK spaces, but I'm clearly out of time. So I should stop here and let everyone enjoy their coffee. Thank you very much for your attention.